Justin said a word on quantum algorithms.
Thanks a lot, Casper. For this talk, you will not have to know anything at all about quantum algorithms. And this is joint work with Mark Bunn, who's here at the Simons Institute for the year, and Robin Kothari, who's at Microsoft Research. So as the title suggests, this talk is focused on query complexity. And in the query complexity setting, there's some known function f on n bits and an unknown n-bit input x. And the goal is to evaluate f on this n-bit input x while minimizing the number of bits of x that we look at. Okay, so the only thing we charge for in the query model is looking at bits of x. So we don't pay attention to runtime or anything other than how many bits of x we look at. So in the classical query model, you can imagine that there's some oracle, and anytime you ask the oracle the question I, it returns the ith bit of x, and that costs you one query. And this talk is about quantum query complexity. And the details of the model are really not going to be important. You just think of it as the classical query model, except now we can query bits in superposition. That's really all I want to say about the details of the quantum query model. But I do want to say something about why we should care about quantum query complexity. And there are really three main motivations for this talk. So one is a motivation from quantum algorithm design. Okay, so although the query model only charges for the bits of the input that you look at, and it doesn't charge for runtime or anything like that, very often quantum query algorithms can be made time efficient. Okay, so the query setting provides a very clean abstraction in which you kind of ignore a lot of the details about making a quantum algorithm run quickly, and you just focus on the query complexity. And then once you have a low query algorithm, it's very commonly the case that you can then make it run fast anyway. And in fact, many of the most famous quantum algorithms were either discovered in or can at least be cleanly described in the quantum query model. Okay, so that's one major motivation for why we're studying quantum query complexity. Another motivation is from classical pack learning. So if you show that a function or a class of functions all have low quantum query complexity, say at most d, then they can all be pack learned in time about n to the d, even in the agnostic model. So the details of that aren't important, but this captures learning in the presence of adversarial classification noise. It's a very challenging learning setting. Okay, so quantum query upper bounds don't just give us efficient quantum algorithms, they also give us efficient classical learning algorithms. And then finally, there's motivations from circuit lower bounds. So if you show that all circuits in some circuit class C all have sublinear quantum query complexity, well, that's a very strong structural statement about C. And in particular, in a black box manner, that tells you that no circuit from C can correctly compute the inner product function, even on slightly more than half of all inputs. Okay, so you prove a quantum query upper bound for a circuit class, and you get out lower bounds, circuit lower bounds against that class. And there are other motivations as well, but these will be the three main motivations for this talk. Okay, so hopefully now you all care about quantum query complexity. So the only real fact about quantum query complexity that I'll use in this talk, and I really won't even use it that much, is the fact that the quantum query complexity of the OR function and the n function is root n. Okay, so a quantum algorithm only needs to look at about root n bits to determine whether at least one of those bits is a 1 or at least one of those bits is a 0. Okay, so classically, we need to look at least a constant fraction of the bits even for randomized algorithms, but quantumly we can do better. That's pretty much the only actual fact about quantum query complexity I'll use in this talk. Okay, so anytime you define a measure of the complexity of Boolean functions, one of the most basic questions you might ask about that measure is how does it behave under composition, under function composition? Okay, so given two Boolean functions f and g, we'd call their block composition just the function you get by feeding a bunch of copies of g into f, where each copy of g is defined on a disjoint set of inputs. Okay, so we're really just composing f and g. That's what block composition means. And it turns out quantum query complexity behaves really nicely under composition. So the quantum query complexity of the composition of f and g is just up to a constant factor the product of the individual query complexities. Okay. Yeah, so this is really nice. Deterministic query complexity also satisfies this property, although that's been known for much longer. Tomorrow, I think Troy Lee is going to talk about whether randomized query complexity satisfies the same kind of notion. So that I believe is still open for randomized query complexity. All right, the point of this slide is just that this is a basic question about quantum query complexity, and it's understood, and the behavior is about exactly what you would expect. Okay, so we totally understand quantum query complexity of block composed functions. So this work is interested in kind of moving beyond block compositions. So we're interested in what we call shared input compositions. So now we're composing F and G, but each copy of G is not defined on a disjoint set of inputs. The copies of G can share inputs. Right, so if you have any such, so this is really some kind of circuit, right? And if you have any kind of circuit like this, there's a trivial upper bound on the quantum query complexity of the circuit, which is you ignore the fact that these copies of G are sharing inputs. This is only like pessimistic. So you can get the upper bound that the query complexity of the composition is at most the product of the query complexities of F and G. That's a valid upper bound, but it might not be tight. So the main question we wanted to ask is it always possible to leverage the sharing of inputs to do better than this upper bound? And our main result is that the answer is yes in a very general setting, namely so long as the inner function is the end function. Right, and also so long as the quantum query complexity of the outer function isn't basically maximal, right, is significantly smaller than n. All right, so as long as these two conditions are satisfied, that is G is the end function and Q of F is sublinear in n, then we can do better than you can do if you ignore the fact that this is a shared input composition. Okay, that's our main result.
So wait, what do we know about the sharing?
Nothing. Just all you know is that there are only n bits of input, and they're shared arbitrarily between the copies of G.
So what's to prevent these n bits from being disjointly shared?
Nothing, but then there can only be, let's just say for simplicity that every copy of G has the same number of inputs and they're all disjoint. Then there can only be, if there are T copies of G, there can only be n over T Gs. And that kind of will limit the quantum query complexity of F. Okay, so kind of, yeah, so here, let me just tell you quantitatively our main result, and then we can revisit the question if it's still not clear. Okay, so our main result is that for this kind of shared input composition, so basically any function on n bits, where the n bits are first fed into a bunch of n gates, and then those n gates are fed into F, the quantum query complexity is at most the geometric mean of n and Q of F, up to polylog factors. So the key comparison point is what is the best you can show if you ignore the fact that these inputs are shared. If you pretend like these are just disjoint inputs. And the answer is if you ignore the input sharing, the best you can show is that the quantum query complexity of the composition is at most the product of Q of F and root n. And this root n is coming because the quantum query complexity of n is root n. Okay, so what we're saving here is a square root of Q of F factor. And that's significant as long as Q of F is noticeably less than n. Right, if Q of F was n, then this bound turns into something actually bigger than n, and that's just trivial because, of course, you can just look at all the bits. Any questions about the main result? Okay, so that's our main result. I'm going to actually spend most of the talk talking about implications of this main result. But I will try to give you an idea of how we show this, actually how the quantum algorithm works. And again, the only fact you'll need to know about quantum query complexity to understand this outline is basically that the approximate degree of the OR function is like root n. And you show that through a quantum algorithm called Grover search, which is capable of searching a bit string and looking for like a one bit in that string. Okay. Before we get to the algorithm, I'll mention we show an analog of this result for approximate degree. So if you just replace quantum query complexity with approximate degree in both sides of this theorem statement, the result is still true. Approximate degree was the notion in Sasha's talk from this morning. I won't say anything else about it. It's related to quantum query complexity, but it's not the same. And the last thing I'll mention is that both results with approximate degree or with quantum query complexity, they're both tight. Actually, there's a simple example that shows it's tight. That example is actually block composed, although that detail is not important. So in general, you cannot improve our composition theorem. Okay, so I'll give you a broad outline of how this algorithm works. So the idea is that we're going to try to look at bits of the input with the goal of killing AND gates that have high fan-in. Okay, so the idea is let's assume that all of our AND gates are monotone, just for simplicity. It's without loss of generality. If we look at an input bit xi and learn that xi is 0, then any AND gates that xi is connected to has its value fixed to 0. Right? So we're going to try to kind of find a lot of 0 bits of the input that are connected to many high fan-in AND gates, thereby killing all of the AND gates of high fan-in very quickly. Okay. So our goal is to basically eliminate all of the AND gates that have fan-in more than n over the quantum query complexity of f. F was this outer function that you're feeding the AND gates into. Because if we do that, then we can, when I say the trivial upper bound here, I mean the upper bound that ignores sharing of inputs still gives us something strong enough. Right? So if every AND gate has fan-in less than n over q of f, then just pretending like, ignoring the fact that the inputs are shared and just applying the disjoint inputs bound, you get that the quantum query complexity of the composition is at most q of f times square root of n over q of f. And that gives you exactly what we want. So we just have to kill all of the AND gates with fan-in more than n over q of f. Right. Unfortunately, we only have this many queries to spend to do the killing. And that's where the rub of the algorithm is. So the remaining challenge is to figure out how to kill all of the AND gates with overly high fan-in, but we only have square root of n times q of f queries to do it. And I only am going to give you like the highest level sense of how we do this because it's a somewhat short talk, and I'd rather talk about implications of the result. The idea is that we're going to iteratively Grover search for these input bits that are 0, but will wind up killing many high fan-in AND gates. So I'm hiding a lot of details here, but there's some kind of accounting argument that we do to both bound the cost of the Grover searches and make sure that each Grover search kills a lot of AND gates. Right, but taking a step back, the high-level outline is actually not unique to this work. We're spending queries to simplify the circuit by reducing the fan in the bottom AND gates. This is a kind of argument that comes up in circuit complexity quite a lot. For example, a prominent example of this kind of argument is in the so-called method of deterministic restrictions. When you see this in circuit complexity, though, typically the goal is not to give a query algorithm. It's to kind of find some input so that you simplify the circuit all the way down to a constant while fixing a few bits of the input. So you see this in random restrictions, deterministic restrictions. Here we're giving an actual quantum query algorithm, which is kind of, in some sense, a stronger goal. And later in the talk, I'll actually talk about some implications that this query algorithm has to circuit complexity. So it'll kind of give back to circuit complexity just as it's been inspired by some arguments in circuit complexity.
Okay. Yeah. Can you say something? If you just care about approximate degree, is there a way to think of this without thinking of the Grover search? Or,
Yeah, so our analog for approximate degree, our proof, right, so let me just go back to where I mentioned it. So the analog for approximate degree, we actually prove with completely different techniques that are kind of just mild generalizations of techniques that have appeared in recent works of my work with Mark and Robin, and also work with Sasha. And we discovered the approximate degree results first, and they're actually completely different than the quantum query techniques. I think we would have never even thought to try to prove the quantum result if we didn't know that the approximate degree result was true, but the techniques are totally different.
Yeah, could you say something about how n over q of f emerges in the proof?
It emerges really just because that is the fan-in we can tolerate, the fan-in of the N gates we can tolerate, to apply kind of the trivial upper bound that ignores sharing of inputs and still get out the result we want. Right? So if the N function on N over Q of F bits has quantum query complexity square root of that, just because of Grover search, and that's exactly what we're able to multiply Q of F by and get this bound. We could try to reduce the fan-in further, but then it turns out we would actually have to spend more than this many queries to do that simplification. So we kind of have two phases of the algorithm, one to simplify the circuit, and then another to just evaluate the simplified circuit. And this bound comes out when you set the cost of the two phases to be equal.
So can you say something about how the number of, so do you have a relationship between the degree of the AND gates that you're trying to find and the query complexity of the first phase, the Grover search?
Yeah, I mean, the paper only works it out with this particular goal in mind, but.
Okay, never mind.
Okay. Any other questions? Okay, so that's our main result about quantum query algorithms, and now I'll spend most of the rest of the talk just talking about implications of this result. Okay, so one implication is a efficient quantum query algorithm for any linear-sized constant depth circuit. Okay, so specifically for a linear-sized depth D circuit, you can get a quantum query algorithm that will only look at n to the 1 minus 2 to the minus d bits of the input. Okay, so for any constant d, this is polynomially less than n. So it's a non-trivial result, since trivial is just look at all n bits of the input. The idea is the following. So we already knew that for depth 1 circuits, which is just like an OR function, the quantum query complexity could be root n. And it was actually shown in prior work of Charles, Cathari, and Kimmel, the depth 2 case, that you can get an upper bound of n to the 3/4 for depth 2. But it wasn't known what the right bound was for higher depths. And so the idea here is that a depth 3 linear-sized circuit is just, imagine without loss of generality, that the bottom layer is N gates, the gates near the input. So you just have the composition of a linear-sized depth 2 circuit and N gates. And you can apply our composition theorem to it, and you get the geometric mean of n to the 3/4 for the depth 2 circuit and n. And that gives you n to the 7/8, and you just iterate. So this actually matches nearly matches a lower bound that was shown in this Charles, Cathari, and Kimmel paper, which is off by a constant factor here. And I'll actually, during the open questions part of this talk, I'll actually come back to this argument and explain how it works. Because an interesting open question is going to be to eliminate this constant factor that's hidden here. Okay, an immediate algorithmic implication of this result is that depth D linear-sized circuits can be agnostically Pack-learned in time exponential in n to the 1 minus 2 to the minus d.
This is on the uniform distribution?
No, this is distribution independently. Yeah, so anytime you have a quantum query algorithm for a class of functions, actually you only need an approximate degree upper bound for the class of functions. You get an agnostic Pack-learning algorithm for arbitrary distributions, and that's what this gives you. Okay, so that's an implication to learnability of circuits. Now I want to mention an implication to circuit lower bounds. This is actually not in our paper. Yeah, this is non-proper learning. So.
But you wrote agnostic to mean non-proper? Or
no, I wrote agnostic to mean it can handle adversarial classification noise. Yeah, so this algorithm will basically find a low-degree polynomial that is, it does L1 regression, L1 polynomial regression to find a low-degree polynomial that is sort of consistent with the training data. Okay. So this implication for circuit lower bounds I'm about to describe is not in the paper, but we'll probably add it to it at some point. So there's an important frontier problem in circuit complexity, which is showing that inner product mod 2 cannot be computed by polynomial size AC0 circuits with parity gates at the bottom. So this turns out to be a special case of a number of really, frontier, long-standing open problems in circuit complexity. It's received a fair bit of attention in recent years. And the best known lower bound is that IP2 cannot be computed by depth D AC0 circuits with mod 2 gates at the bottom of slightly superlinear size. So you need size at least n to the 1 plus 4 to the minus depth. Okay, so we think the answer is probably you need super polynomial size. We can show slightly superlinear size. So there's a big gap between what we think is true and what we can show. So an implication of our results for linear size AC0 circuits is kind of a twofold improvement over this prior work. So one improvement is we can improve this 4 to the minus d to 2 to the minus d. So it's even slightly more superlinear, but maybe that's not so interesting. Qualitatively, it's a little more interesting maybe that our lower bound holds even for, it's a correlation lower bound. So it holds even if the circuit only computes inner product mod 2 correctly on slightly more than half of all inputs. So I guess I have about 5 minutes left, which is the right amount of time to say a little about open questions. So one interesting open question is our upper bound for depth D linear size circuits tight? Okay, so we know our composition theorem is tight, but it's possible that you can prove an upper bound for depth D linear size circuits without going through that kind of composition theorem. Our upper bound nearly matches a known lower bound, but there's this constant factor gap in this exponent of the exponent. It'd be interesting to close that. As I'll explain on the next slide, one way to accomplish this, I think probably the right way to accomplish this, is to exhibit a quadratic size DNF with essentially maximal quantum Fourier complexity. Right, so I'll explain in a second on the next slide why that would be enough. Yes, so we'll come back to that. Alternatively, if you could show that every quadratic size DNF has sublinear quantum Fourier complexity, I think that would be very surprising and extremely interesting. Right, so regardless of whether resolving this question will achieve the goal on the slide, the resolution will be interesting. We either achieve the goal on the slide this way, or you have a really, really interesting quantum Fourier algorithm. OK, so let me explain why understanding quadratic size DNFs is enough to understand linear size AC0.
Just for contrast, if it was linear size DNF, then we have square root of n query complexity, or no?
So a linear size DNF, we know an upper bound of n to the 3/4. That was actually shown by Childs, Cathari, and Kimmel, and our work kind of recovers that and generalizes it. We don't have a matching lower bound. So there's a lower bound that's better than root n. It's something like n to the 0.56 or something. So there's a gap also for linear size DNFs. But if you resolve this question, then about quadratic size DNFs, you would also resolve the question for linear size DNFs. And I will explain why right now. OK, so Beame and Machmouchi showed several years ago that there's a depth 3 AC0 circuit of quadratic size called the surjectivity function. Its definition won't be important for this, which has essentially maximal quantum Fourier complexity. And then Sasha more recently actually showed it's truly maximal. Right? Sasha removed the log factor from the lower bound. OK, so there's this transformation by Childs, Cathari, and Kimmel. What they do is they show how to turn basically a quadratic size circuit of high quantum Fourier complexity into a linear size circuit of nearly the same quantum Fourier complexity. Right? And that's why this question about quadratic size DNFs turns out to be related and basically almost equivalent to the question about linear size DNFs or circuits in general. So let me tell you that transformation. Okay, so C here is a quadratic size circuit with maximal Fourier complexity, and we want a linear size circuit with high Fourier complexity. So what you can do is you can look at the quadratic size circuit but defined only on root n inputs. So now that's a linear size circuit in n. And then you can compose that, block compose it with the n function on root n inputs, and now you actually have a linear size circuit on n inputs. And we understand how quantum Fourier complexity behaves on the block composition, and the bound that comes out for this composition is exactly the product of n to the 1/2 and square root of n to the 1/2, so n to the 3/4. So that gives you an n to the 3/4 lower bound for what turns out to be a depth 3 circuit. So this is depth 3, but the bottom gates are end gates, so when you compose it with end, it's still depth 3. And then you can iterate this argument. So now you just look at the block composition of surjectivity on n to the 1/2 inputs with this linear size thing from the previous stage on n to the 1/2 inputs, and it improves the lower bound to n to the 7/8, but now it's depth 5 instead of depth 3. And you just can keep going. So this like bootstraps a lower bound for quadratic size circuits into a lower bound for linear size circuits. And the only reason it doesn't match our upper bound is because the quadratic size circuit with maximal query complexity was depth 3, not depth 2. Okay, so if you had that lower bound for depth 2 quadratic size, you would match our upper bound. So I think that's an interesting question. Okay, and now do I have like, is that clock slow? Do I have 2 minutes?
Yeah,
That clock is fast.
Fast? Okay,
4 minutes
yes,
fast.
that's better than slow, yeah. Okay, so maybe I'll get through 2 more questions. Okay, so it would also be interesting to generalize our composition theorem in some way. So maybe it holds for functions more general than just the n function here. Something I wanted to mention is that you have to, if you're going to try to generalize this, you have to be careful because it turns out if you try to reverse the roles of f and n, so if you look at an end of copies of f instead of an f of copies of n, then this result turns out to be completely false. And actually, the counterexample there is surjectivity, but I won't explain why that's true. It's not 100% obvious how to map surjectivity into this. So there are probably generalizations of this you can prove of our result, but you're going to have to be careful how you do it. For example, you can't just reverse the roles of f and n, or you can't show anything non-trivial. Okay. Right, so I described some classical implications of our quantum query upper bounds here to learnability and to circuit lower bounds. And I think it'd be interesting to try to discover more to identify other implications of these kinds of quantum query upper bounds. So if you show that a circuit class, every circuit in the class has sublinear quantum query complexity, that's like a really strong structural property of that circuit class. It just should be broadly useful. So for example, I have no idea if it's possible to use such a statement to get faster satisfiability algorithms. But you could imagine maybe it is, just because it's a strong structural property. So I think that would be an interesting thing to explore. And then finally, I guess my last question is, can we move beyond like linear size AC0 circuits? So we showed slightly better lower bounds for AC0 mod 2 circuits. Is this a path towards actually showing super polynomial lower bounds for such circuits? That would presumably require showing some kind of polynomial approximability result for all circuits in this class. And maybe I'll just stop there, and if you care to, you can just read the last 2 bullet points on your own. So thank you.
Any questions?
How do you obtain this fact that IP2 is not in the 0 from your approximate degree or 1?
Yeah, so I believe this is folklore, but you can at least, I know that I had a citation somewhere. Avishai, in his paper, recent paper on better bipartite formula lower bounds, uses this connection. So if a circuit class has sublinear approximate degree, you can show that even when you compose it with parity or anything of low rank, basically, that circuits in that class have to correlate well with some parity. And we know IP2 doesn't correlate well with any parity. Essentially, that's the argument. Does that make sense?
This thing.
Thank you.